Hello everyone. Today I'll be presenting our work, Select, Secure and Lightweight Context-Aware Mechanism for Smart Vehicular Networks, authored by Trupil, Limbasiya, myself, Arijit, Karati, and Debasis. I sincerely thank the organizing committee members for accepting our work at the IEEE DASC 2022 conference. Here are the contents of our work. First, I'll be discussing smart vehicular communication systems, followed by the limitation of existing protocols. Then I'll discuss our contribution and the proposed protocol in detail. Then I'll be discussing adversary model and certain security assumptions to show our scheme resists all known security attacks. Finally, I'll discuss about the performance evaluation and the comparison. The Intelligent Transportation System, which is known as ITS, relies on vehicular networks to transfer on-road data between vehicles and the roadside unit. It facilitates travelers with various vehicular context-aware applications and services such as real-time traffic management, road safety, infotainment, edge computing, and remote diagnostics for a more safer and comfortable journey. Here we can see the figure which discusses a high-level overview of vehicular communication system that comprises with three entities: smart vehicles, RSU, mobile device user, for three distinct communication, which is known as vehicle-to-vehicle communication, vehicle-to-RSU communication, and mobile device to RSU communication. When a vehicle is registered, an on-board unit is initially installed with a fixed processing capacity and memory to conduct various tasks, including different kinds of computation, communication, and data verification while the vehicle is in motion. The RSU, the next component, which are deployed on the roadside to share relevant information with vehicles and mobile users through dedicated short-range communication standard, which is known as DSRC, Wi-Fi, or even with 4G, 5G. In such kind of communication platform, mobile users are mostly interested in predicting situational roadside data for better citywide commuter services. As we can see in this picture, there are three communication, 1, 2, 3. All these communication are going to take place in public mode. That means an attacker can play with all such transmitted message. It can change the data, it can hijack the session, it can modify the data and everything. So we have found some security vulnerabilities that are possible in this vehicular communication. Smart card, stolen smart card or OBU, session key disclosure, modification, replay, password guessing, user impersonation, and vehicle sensor impersonation. Under all such attacks, attacker actually tries to play with publicly transmitted message and try to reveal some sensitive information. And through that sensitive information, it tries to perform some attack. We have studied some related work, and we found that these 6 related works are very competitive, and even though they have some features, they are vulnerable to certain attacks. For example, work 20 is vulnerable to smart card lost attack. Work 24 is vulnerable to replay attack, and so on. So in this context, we have contributed with a communication protocol, which is named as Select. The Select is designed for resource-constrained devices using low-cost cryptographic operations such as bitwise XOR operation, concatenation, and SHA 256. The security strength of the Select are analyzed against crucial security attacks, and we found that our protocol actually resists all such listed attacks. We evaluate the result of our protocol under some test-bed analysis using Raspberry Pi Model 3. Now we move to the proposed protocol. The proposed protocol considers SHA 256, XOR operation, concatenation operation, which makes our protocol very lightweight without compromising the security. Our protocol supports V2V, V2R, and mobile device to R communication. It includes 6 different phases: initialization setup, mobile device registration, vehicle sensor registration, which are executed once, while MDD V2R communication, V2R and V2V communication, which are going to take place very frequently. Coming to initialization phase, here we consider registration authority as trusted third party, which generates first 256-bit private key, and then it chooses the random number and the time stamp, and then it computes KSI with the help of these three parameters, and finally it computes the VCK. And time to time, RSU, the roadside unit, receives some information from the registration authority, and these information actually it receives, and we'll discuss how to generate those information in the later of this section. And finally, we consider this time sync protocol for sensor network to achieve no energy time synchronization. Here, the mobile device registration phase. Here, user first chooses ID, selects ID, password, and RNI, and then it computes EID, hash password, and then it transmits this EID and hash password to registration authority, and registration authority choose one nonce and compute XI and WI with the help of its own private key, KSI, and the received information. And then it sends those information via smart card data as a smart card data. And by the time mobile device user computes HID and HNI and YI. And on receiving this smart card data, it computes ZI, which is nothing but has HID XOR WI XOR YXI XOR hash password, and then it removes the XI from the smart card and updates the smart card by with the values YICI HNI in the smart card. In the next registration, that is the vehicle sensor registration, where vehicle transmits the ID and the registration authority chooses one nonce, and then it generates one unique key as like this and the anonymous identity as like this, and finally it transmits the unique key VCK and AID to the vehicle, and that this data will be installed in this TPD. At the same time, registration authority saves this UKK, IDK, and AIDK in its secure database. Now coming to this MD2R communication, here user has this all information, ID, password, DT, and this smart card data. And now it inserts the smart card and receives the data, and it provides the ID and the password, and then it computes certain values and the parameters as like this, and it checks whether this computed value YI prime is equal to smart card data or not. If it matches, then it will choose one nonce, and then again it will calculate certain parameters, and finally it sends this PID, AI, MUSI, P1, and T1 to RSU. And RSU calculates its freshness, and then it again checks whether certain computation are getting matched or not. And if it match, then only it generates this NSJ, and finally it computes DI, CI, DI, and the session key. And then it transmits this DI, CI, and DI, PI and CI with the timestamp 2 to this user, and user actually checks the freshness and then finally generates this session key. And interestingly, we can consider that we can observe that this session keys generated by this RSU and the session key generated by this user I both are the same, and it is correct. Coming to the next communication, that is V2R and V2V communication. Here we'll discuss first V2R communication. This is the figure 1. RSUJ regularly scans the network interface to know all in-range vehicle with their IDK, and a vehicle sensor continuously sends message, and then it sends this QK as like this with the help of the along with this anonymous ID, and then it checks the freshness, and after that it computes certain parameter RK and SK as like this, and if both these parameters are getting same or the matches, then only it just consider the message, otherwise it discards the message. Now coming to the next figure, that is figure 2. Here a vehicle sensor frequently sends the traffic and road safety messages to in-range vehicles using DSRC protocol, but the receiving vehicles should check the authenticity of the data, whether it is valid or not, or it is correct or not. So when VSK enters into the range of RSUJ, it gets the TRK. TRK is a one value, one parameter sent by the RSU. And with the help of this TRK and its private, like its secret key, VCK, it encrypts the message and provides the alpha K, and the beta K is the hash value of this information. And then it sends certain information to another vehicle. The vehicle computes and checks whether this timestamp is fresh or not. If beta K is equal to beta prime K, then only accept the message, otherwise reject it. Security analysis. The proposed protocol supports a wide set of security properties. However, due to time restriction, we are skipping this part. The security features comparison will come back again. However, I'd like to say that our proposed protocol supports 128-bit symmetric security. Performance analysis. The proposed protocol is executed on Raspberry Pi device. This is the configuration of such device. And we compare our scheme with other scheme, and we found that the proposed scheme considers 0.8320 millisecond and 10.4 millijoule in terms of energy. And also in terms of communication, it takes nearly 3000 bits, and in terms of storage, it requires 2000 bits. So the proposed protocol supports actually resist all the security attacks and also requires less computation cost, which is very much near to GOP et al. Right? So here we can see that the proposed protocol actually is better because GOP et al. Does not support these A1 features. And also in terms of communication, it actually requires much more higher communication cost. In summary, we have designed one effective data exchange protocol which resists wide set of security with adequate overheads. Here are the references. Thank you very much for your attention. If you have any queries, you can contact me.